So, hi everyone. My name is Jamit Vasau, and this is machine learning using Python, a recommender system. This is module 10, part 2, and this is session 20th. So, this is going to be the last session for the machine learning using Python. And we'll be concluding this machine learning using Python course. So, let's get started. Before we move to the today's session goals, let's just see what we did for the previous session. So in the previous session, we discussed about the recommender system, what are recommender systems and why they are used and how they benefit the business on various social media platforms or other e-commerce platforms. In that, we discussed about association rules, where we associated one item with another and predicted which items are more likely to be added after some items are added, or if one item is added, then which items are more likely to be added. Now, in this session, we'll be discussing about collaborative filtering. So in collaborative filtering, we'll be discussing about the user-based filtering, content-based filtering, and then we'll be using the surprise library from scikit-learn. And in the end, we'll be discussing about the matrix factorization. Now, all of these are very important when we talk about recommender systems, as they are actively used, and they tell us about how the social media or the e-commerce platforms use the data in order to cater the customers in a very personalized manner and make the recommendations very effective. So collaborative filtering, it operates on the basis of if similar users have bought similar items, then their interest must be similar. So when we talk about users being similar and them buying similar items, then it becomes a user approach. So the association rules that we discussed in the previous one, they fall short on this thing, that they do not take customer feedback. Now in association rule, we talked about if one person is buying a certain item, then what is likely to be the next item. Now after the purchase, if the customer didn't like that item, if customer purchased 2 items and out of them one of it is not something that the customer liked, or one purchase was something that the customer didn't like, then recommending that item again to the customer becomes ineffective and makes an ineffective recommendation. So this is where the collaborative filtering comes in, because it takes into consideration about the customer feedback and solves the drawback that association rules has. Now association rule, it does have the advantage of having a clean data and being easy to interpret and work with, but collaborative filtering makes an advanced job of taking the customer feedback. So collaborative filtering helps us to recommend customers with a more customized or personal service, and having an overall an improved and a better user experience by taking into consideration the user's sentiments. So for example, let's say there are similar users A and B, both of them have similar taste, and because user A loved the product M then the user B, which is similar to user A, can be recommended that product M. Same goes for videos. If user A and B are similar users, user B likes video X, video Y, and video Z, and because they are similar, that video Z can also be recommended to user B, user A, sorry. So how to find similar users? So we are taking this example of three people, Purvi, Rahul, and Gaurav. And three of them have a certain kind of book purchases. And based on their purchases, if we can tell how they are similar. So when we compare it in a Euclidean space with two books into thin air on y and Missoula on x-axis, then and plotting them on the Euclidean space, the distance between Rahul and the Euclidean distance between Rahul and Purvi is shorter. So the recommendations that can be made for Purvi can be made for Rahul as well. And the same goes for Rahul and Purvi, vice versa. So if the users are similar, then the similarity measures such as Jaccard coefficient and cosine similarity will have the value closer to 1. And the distance measures such as Euclidean distance that we just previously saw can have a low value when the similarity is more. Now, mostly used similarity distance or used distance are Euclidean, Jaccard coefficient, cosine similarity, and Pearson correlation. Now, collaborative filtering type have two types, which are user-based similarity and item-based similarity. And as we have introduced ourselves with the collaborative filtering, it's very easy to guess what they mean. The user-based similarity means that if some similar users are buying some common items, so basically finding k similar users based on the common items they have bought, and in item-based similarity, finding k similar items based on common users they have bought. Now these algorithms are similar to the k nearest neighbors. So to understand, we'll start with user-based similarity, where we find similar users on the commonly bought items. So we'll be using the data set. You can see the link on the data set, and which is a data set about finding similar, and we'll use that data set for finding similar users based on common movies the users have watched and how they have rated those movies. So we have users and the rating of those users on those movies. So this folder of movie ratings contain one of the file called ratings.csv, which contains the following features, which are user ID, movie ID, rating, and timestamp. And the ratings are on the scale of 1 to 5. So when we read these movies, ratings.csv, and display the first few records, this is how the data set looks like. And we have user ID, movie ID, rating, and timestamp. Now, timestamp is not something that we are going to use, so that's why we will be dropping timestamp. Now, now there is something, there is a method called pivot method, which takes three parameters, which is index, columns, and values. So uh, we are making a user movies DF and storing the pivoted method used rating DF that we first built. For the index, we will be using the user ID. For columns, we will be using the movie ID. And for values, we will be taking the ratings that are present. Now, when we display the records from 0 to 5 for the columns 0 to 15, or from the for the movie ID 0 to 15, remember that this is the here the columns are movie ID. So after movie ID, these are the movie IDs 1 2 3 4 till 15, and the user IDs are the rows which are displayed over here from 1 to 5. So when we display this user movies DF after using the pivot method, you can see that the ratings that user have not made for the movies are shown by NaN values. So we want to replace these NaN values with zeros. So we'll be using the fill NA method and replace it with zeros. And you can see that the values of NaN are replaced with 0. Now we'll be calculating the cosine similarity. Now to calculate this cosine similarity, we'll use the scikit-learn matrix dot pairwise distances. Now pairwise distances, they take x, which is a data, which can be a data frame or an input array. The y, if you are comparing a data frame with another data frame, then y will be the other data frame, but it's an optional one. If you are using another data frame, then it's useful. Then comes the metric, which takes in different kinds of distance matrix. Here by default it's Euclidean, and if the keyword arguments are allowed, then it takes the additional keyword arguments. Here we are using the cosine similarity. So cosine similarity closer to 1 means users are similar, are very similar. Sorry. And closer to 0 means they are very dissimilar. So using the user similarity and pairwise distances, and storing the user similarity into a DF called user sim DF. And when we when we display these the result that are stored and into the DF, you can see that the snapshot of it is being displayed on the bottom right. Now user 1 is going to have the most similarity with the user 1. User 2 will be most similar with user 2, and user 3 with user 3, and so on. So each and every user will be the most similar to itself. So this is not something that we want. And because of that, we'll be changing those values of ones, which is the most similar in a diagonal way, to zeros. So using the numpy dot fill diagonal, we'll be filling the ones with zeros in the diagonal, and which helps to avoid selecting self or the user itself as the most similar user. Now filtering the similar users. So user simdf has a index max and x is 1. When we print the most similar user for the first 5 users, then 266 for user 1, 366 for user 2, 313 for 3, and 491 for 4, and for user 5 it's 470. So let's take more detail on by selecting a single row. So by selecting user 2 and watching the scores of user 2 for users from user 330 to 340. So you can see that down below, user 2 is most similar with user 331 in that split or in that slice. So with 331 and 339, and it's least similar with user 337. Now, based so for user 2, it was 331 and 339. It can be because those are the people that have watched similar kind of movies and rated those movies in the most similar way. And for user 337 and user 2, they might have the most dissimilar movie taste, and hence watched movies that might not be similar to any of them, or very less movies might be similar to them, and they have rated more dissimilar scores on the commonly watched movies. So to check how we described our intuition on why those scores were similar, we'll be using another dataset called movies.csv. Now movies.csv, when we read it, you can see that it contains movie ID, title, and genres. Now genres is not something that we are going to use, just like last time we dropped timestamp from it. This time we'll be dropping genres from it. Now, to get the most similar similar movies between two movies, we'll be defining a method called get user similar movies, which will take two users as an input and give us the output. So when when we use common movies to store those values and get and use the method of get user similar movies and give user ID 2 and 331, which were the most similar ones as we saw, and just to short the amount of list, we are only taking the movies that both of these users, user 2 and 331, have rated above 4. So you can see that user ID 2 and movie ID and the ratings that user ID 2 has given, as well as user ID 331, the ratings that they have given, and the title of the movie. You can see that why we imported another data set called movies, because it had the titles of the movies along with the movie ID. Now, the another user that was similar to user 2 was 339. So you can see that when we display all the movies that are common to both of them, irrespective of the rating that they have given or commonly watched. So these are the movies that are common to both of them, and you can see that ratings given are also mostly common and fluctuates around the difference of 1 or 0.5. Though this is only a an observation and not something that is confirmed. Now, now we have checked the similar users. The dissimilar users are were user 2 and user 337 in that slice that we have taken. So, as you can see that when we use the common movies for user 2 and 337, the only common movie is Shawshank Redemption, and one of them has rated 5 and another one has rated 3. So, and you can see why they were the most dissimilar in that slice. Now, we have used user-based filtering. And in user-based filtering, the one thing is that you have noticed, you might have noticed, is that we already had the taste of the user figured out from the dataset that we used in order to get those insights. We already have those past historical data or past interactions from a user. Now, in recommender systems, there is something called as cold start problem. Now, cold start problem occurs when a new user has joined the platform. So here I'm talking about any platform. So let's say if a user has joined on YouTube. Now YouTube doesn't know that what is the taste of the user. That is what is called a cold start problem, that the platform does not know exactly what to be recommended to a user because it does not have any past data or past historical data of the user to recommend that user and cater the customer with the customer centric preferences. So one way to solve the cold start problem is that use item based similarity. So if certain items are bought by many users or are similar, have similar ratings among users, those kind of items can be recommended to a totally new user. And after the interaction of user with those products, whether they click on it or not click on it, we can build up some kind of data in order to cater the customer. Now, item-based similarity is a technique that is used in a recommendation system that analyzes the relationship between products based on the user behavior, particularly focusing on how frequently items are purchased together. So these things, these kind of things are already used by a lot of platforms, maybe e-commerce, some OTTs, or not some, but a lot of OTTs and many social media platforms. A simple example to start with is that if someone has bought a smartphone, then they are more likely to make a purchase on a specific case and a screen protector for the smartphone they have purchased. A similar kind of thing, a similar kind of thing happens when we shop at Amazon. If we have, you can see the snapshot of it on Amazon, for Amazon too. If we have bought a book, similar kind of books are recommended to us on customers who bought this item also bought segment. So these kind of recommendations that are done, even Netflix has it. YouTube constantly recommends us with similar videos that we might be interested in. Now these kind of uh, recommendations helps these business improve the sales, as we are catering the customers for their own preferences, meaning they are getting more improved customer satisfaction and increased sales for the platforms. So as we have used item-based similarity, item-based similarity, uh, discussed item-based similarity now, we'll be calculating the similarity between movies. So, so here we'll be using the movie ID as index and user ID as columns. Now, rows represent movies, columns represents users, and the cells in the matrix represents the ratings users have given to the movies. Now, again, we'll be using the pivot method for index columns and values, and for replacing the NaN values with zeros, and then using the pairwise distances for metric correlation. Here, the 1 minus pairwise distances is done in order to convert the correlation distance into similarity score, allowing for a clear, clearer interpretation of how similar the movies are based on user ratings, which helps us to know how closely the related movies are. So we'll be using movie sim to store those values and movie sim df to store all the whole to make the whole data frame and store all the movie similarity score. So when we use this movie sim diff and display a few of the rows and columns, you can see how the on the similarity score looks like. When we use the shape method in order to get the dimension of the data frame, you can see that there are 9,724 rows and columns. Now we are using the similarity score. So if the correlation distance is 0, the similarity score becomes 1. And if the correlation distance is 1, the similarity score becomes 0, indicating no similarity. So finding the most similar movies now from as we have movie sim diff, we'll be defining a method called get similar movies, which will take movie ID and return the similar movies based on the cosine similarity. Now movie ID and the index of the movie record in the movies DF are not same. So what we want is the index of the movie record from the movie ID and use that to find the movies similarity DF. So find the similarities from the movies similarity DF. The other thing is that it will take an optional parameter top n for top similar movies. So when we display the movies similarity, so the snapshots that you are watching below are for movies DF and movies sim DF, just in order to keep the track on what we are saying, as the names are very similar and it can be easily get confused. So movies sim DF is the one on the right and the movies DF is the one on the left. So moving further, finding the most similar scores, we'll be checking for the movie ID 858. When we check for the movies DF and having the ID 858, refers to the movie title The Godfather. Now will be using the get similar movies to 858. When we use that, you can see that similar to Godfather, the other movies are The Blues Brother, The Third Man, Paris is Burning, and Dirty Dancing. So users who watched Godfather will have also watched Blue Brothers and so on. Now we'll check for another movie with movie ID 231, which refers to the movie named Dumb and Dumber. So getting the similar movies for the movie ID 231, you can see that all of them, the way they were rated. Now, not necessarily that all the movies belong to a comedy genre, but there is a chance that most of them will be belonging. Can be belonging to the comedy genre. So, just to get a recap of it, we started with collaborative filtering and item-based filtering, for which we used ratings of users. So we used this DF. After that, we dropped timestamp because we are going to use it, and this was how the user, the DF looked like after that. To get the shape as well as the unique values of the ratings, sorry, the user IDs as well as the movie IDs are these. So creating a pivot table or a matrix, we have 610 users and 9,724 movies. So a matrix size will be this. After creating the pivot table, where the rows represented the users and the columns were movie ID. These were the movie ID. We replaced zeros with nans with zeros, and then used a pairwise distance in order to calculate the cosine distance. Calculated the cosine distance, and here we checked about which are the most similar. So to user 1, it was user 266, user 2, user 366, and so on. We wanted to get specific. So for user 2, in the slice 330 to 340, which are the most similar ones. So in order to get the titles of the movies, as we only had the movie IDs, so in order to get the titles of the movies, we used another dataset called movies.csv and stored it in movies.df. Now, after having the titles and writing the method for get similar movies and using the common movies, we used the similar to user 2 and user 331. These were the movies that were common to both of them, and that they were rated them above 4. After that, it was user 339, and then for most dissimilar user 337. Now again, defining the method for get similar movies and an optional parameter of top n, sorry. So we used, because we were discussing these in item-based filtering. So before this, we were actually discussing user-based filtering. So in item-based filtering, we first looked after the movies that were similar. So movies that were similar to ID 585, 858 was Godfather, and similar movies to Godfather were these. And for another ID 231, similar movies were these. Now we'll be using something called as a surprise package from scikit-learn. Now, so surprise package. So for a real-world implementation, we need a more extensive library which hides all the implementation details and provides an abstract application programming interfaces to build recommender system. And for that, surprise library is used. So two things that they provide is that it provides with a lot of algorithms and similarity. Metrics for different distances, as well as similarity measures or evaluation metrics. And it also provides some methods to recommend. So starting with surprise and importing dataset reader, KNN basic, evaluate, and accuracy. Actually, evaluate is something that is not used. So evaluate is not something that we are going to use, as it's a deprecated feature. So dataset is so starting with dataset, it's a class and which is used to load datasets into surprise library. It provides the methods to handle and prepare data for building recommendation models. Readers, it helps to define format of the dataset, including the rating scale. It specifies how the ratings are structured and their minimum and maximum values. KNN basic is a k nearest neighbor algorithm, and accuracy is functions to calculate the accuracy metrics for evaluating the performance of the recommender systems, which are precision, recall, and F1 score and stuff. So using the reader on rating scale 1 to 5, data for loading the data, loading from the rating DF, and the columns that we are going to use, as well as a reader. Now, to use the user-based similarity algorithm, the surprise prediction algorithm KNN will be used, which takes the following parameter, which is k, minimum k, k neighbors, the maximum k neighbors, the minimum k neighbors, and the sim options, which is a dictionary of name and user based. The name contains the name of the similarity to be used, and the user based true for the user-based similarity and false for the item-based similarity. So we use the item-based cosine sim for Pearson, and user-based equals to true, and then using the KNN for it. We can also use the grid search CV here. So using the grid search CV for KNN, the data it takes and the measures for on which we want to evaluate it, and the CV value or the k-fold cross validation value or the k value of 5. When we run this using these parameters, we get the value of 99.9909, which is the root mean square error. Now it's a pretty good model, but is there a way to find a more better model than that? So here we have used cross validate. Now we'll be using the grid search CV. So the algo class will contain the class of the algorithm to evaluate. Parameter grid will take the dictionary with hyperparameters as keys and list of corresponding possible values that will be used to search optimal parameter values. And all the combinations will be evaluated with desired algorithm. The measures measures the measures that are taken for evaluation of the model, the CV value, again the k value, and refit. If true, the refit it will refit the algorithm on the whole data set using the set of the parameters that gave the best average performance. If false, it does not refit on the whole data set. So the grid search CV method will return the best model and its parameter. So for a guideline, we can use the number of neighbors as 10 to 20, similarity indexes as cosine and Pearson, and the user-based or item-based similarity. So with those parameter values, the k value is 10 to 20, then name for similarity options in name, cosine or Pearson, and then user-based true and false, both of them. Moving ahead with these on the grid search CV and fitting the data in grid CV model that we have prepared. When we get the score, we get the score of 0.9963, and the best combination that we got was cosine similarity and the user-based equals to 2, as well as k value of 20. If you want to capture more details about the CV results, then we can use the CV results by converting it into a data frame. And you can see that parameter k taking different values with the similarity scores as well as the user-based approach, true and false. And you can see the best or the rank 1 was given to at index 0. Now as we have found the best model, now it is time to make the predictions. So mathematically speaking, Ri is the rating of the nearest user, Ui, and there are k nearest neighbors. Si is the similarity between user and the neighbor. So the prediction will be given by R equals to summation of Ri into Si from I equals to 1 to k divided by summation of Ri for I equals to 1 to k. Now, for that is mathematically speaking, but we have a predict method in the surprise library, which takes the user ID and movie ID and predicts the ratings. Now, in the ratings, there will be something called as a EST, which states the estimated value of those ratings. So when we use the grid CV and predict for user 1 and 2, we get the estimated rating of 2.55. So before moving to factorization, we installed this scikit surprise, used KNN, then I used use the sorry, the KNN basic for k equals to 20. The minimum k neighbors were 5, and the dictionary which contains the distance and the user based, for which we when we run it over here, we get it 0.97. Now, in order to get a more better model, we did it with different values, and we checked it with combinations using the grids of CV with cosine and Pearson, as well as the values of user based true and false. Now, getting those scores, we get the 9.9742 and the other parameters of k, and as well as the name and the user based. After this, we are trying to make the prediction, and we made the prediction for user 1 and 2. So for user 1 and 2, we got the similarity score of 3.72. Now we'll be discussing about matrix factorization. So matrix factorization is a matrix decomposition technique which helps us approach for reducing size of the matrix into its constituent parts. Now, matrix factorization algorithm decompose the user item matrix into the product of two lower dimensional rectangular matrices. Sorry. So, for example, we have this user movies rating matrix. Now, the M1 to M5 are the movies, and the U1 to U3 are users. So the values that they are containing are the ratings that the users have made on those movies. So when we create these users factor matrix and the factors movie matrix, so the user movies matrix is factorized into 3 user factors matrix, the first one. And just a second, I think it's getting confusing for no reason. So now we have the reference to user movies rating matrix. So that user movies rating matrix is factorized into 3x3 user factors and a 3x5 factors movies matrix, which are on left and right respectively, as I mentioned. So the user movies matrix contain ratings from 3 users, user 1 user 1 to user 3, and for movies M1 to M5. The idea behind matrix factorization is that there are hidden or latent factors influencing why users rate movies the way they do. These factors could relate to aspects like the story, actors, or other attributes of the movies, but we may not exactly know what they are. So we can call, and that is the reason we call them latent factors. So the matrix of size NMN, where n is the number of users and m is the number of movies, can be broken down into matrices of size nk and km, where k represents the number of latent factors. So the user factor matrix represents that there are three factors and how each user has preferences towards these factors. So factor movies matrix represents the attributes the movies possess. So some of the observations you can see is that U1 has the highest preference for factor F2 in the user factors matrix, which is on the far left. The user 1 has the highest preference for factor 2. For user 2, it's factor 3. And you can see why. Because if we look at the factors movies matrix, comparing the users factors matrix, you can see that uh, factor 1 has a highest value for M3. Sorry, very sorry. So user 1 has given high ratings to movie M2 and M4. So one of, yeah, so, also, sorry. Oh, sorry, I was confused with F1 and F2. So user 1 has the highest preference for factor F2. And when you see factor F2's value in the factors movies, you can see that M2 and M4 are the highest one, which are also the highest rated by user 1. Now we cannot know exactly why, but you can see the pattern over here and the similarity over here. So one of the popular techniques for matrix factorization is a singular vector decomposition, which is SVD, which takes the parameter as a number of factors called n factors. Here we'll be using the 5 latent factors for SVD and use it with cross validation of SVD for, so we'll use the cross validate for the model SVD, the data, and the measures as root mean square error, the CV value as 5, and the verbose equals to true. And you can see that for those folds of 5 folds that we have done, the mean value that we get is of 0.8906, which is better than the earlier algorithm. Now let's look at the Jupyter implementation for matrix factorization. We used SVD for n value n factors equals to 5 and use the cross validate for the model SVD, data, and measures. And you can see that we get the mean value of 0.86 over here when we run it. So this was it for this was our session for collaborative filtering, where we started our discussion with user-based filtering. Then we discussed about the content-based filtering, as we wanted to address a problem for user-based filtering of cold start problem. So that's why one of the approach that was feasible for us was that can be used was the content-based filtering. And after content-based filtering, we used a surprise library to which helps us ease out all the implementation or hide all the implementations and help us design a recommender system very easily. And after that, in the end, we discussed the concept of matrix factorization and saw how uh, it is used and how it can be interpreted. So this was it for the course machine learning using Python. And the data set is over here, and you can download it from over here. And the link to the surprise uh, library of Python, you can read it in order to get a deeper understanding. So this was it for from our side. Thanks to everyone who attends. Thanks to everyone from EOTF who helped me, Prakash sir, and everyone. So I'm Jaimit, and thank you for going through the lessons. Thanks.